All right, so then I will quickly go to the exercise and briefly show the exercise. All right, so the first part of the exercise is simply use the code and run it. And then, which is actually very important for using Song, is to look at the different precision settings and find precision settings that you can run on the computational power that you have available. So here the idea is that you change the most important precision parameters and find something that is runs on a reasonable time on your machine, which for this exercise should be like maximum few minutes, because you have 1 hour. So if it takes 10 minutes to run the code, that's too slow. Then the next part here is looking at the intrinsic bispectrum and then turning on different effects like add polarization, turn off polarization, add experimental noise, which is documented in the ini file, how you can do that, and then see how the intrinsic bispectrum and the signal to noise change with respect to these parameters. And then finally, the code outputs a file automatically which has the signal to noise as a function of L. And then if you use the different settings, you can create kind of this plot. Only that, of course, here we go up to 4,000, and in the quick run, you go up to 100. So you will, unless you have a very, very fast machine, you will probably zoom into this corner of the plot here. Then there is an option for storing runs, which is extremely useful if you want to redo some things and not waste a lot of time. So the code can, in fact, store essentially everything it produces. And then at a later run, you can run on the folder to import all of this data, and you don't have to redo the calculation. And this, for example, is very useful if you only want to make changes to transfer 2.c or things that are in transfer 2.c that do not affect anything in perturbations.c. Then you can simply store the sources of perturbations 2.c, and you never have to rerun this module anymore. Then finally, this is an exercise about visualizing the output. Because ideally, we want to, in the code, you can get these Fourier bispectra for kind of all different perturbations here for CDM, but you can also look at different perturbations from cold dark matter, baryons, whatever you want, all second-order perturbations. You can look at them, and the code has some output structures, how you can quickly generate human-readable files that you can then plot. And then here there's some exercise about the sampling that is needed to get large-scale structure observables. Okay, so these are the exercises, and then I think I'm finished now, and you can already start with the exercises. Okay.